Welcome to the intertemporal markets, intertemporal asset pricing market models. We're going to look at Brown and Gibbons to start off with. Brown and Gibbons make a very profound statement, right? And that they say that asset return should be exogenous rather than, should be endogenous rather than exogenous. Therefore, it's good to look at utility-based models because they allow you to be silent on the distribution of returns. It makes a lot of sense. It is silly to assume a specific distribution like multivariate normality, right? So the returns themselves should be endogenous and should come from the model. Okay. They're going to look at power utility function and particularly the situation where the power is 1. In that case, it reduces down to log normality. Okay. So this is just some intuition to get the Lucas model, which is studied in finance theory. Essentially, you get that the price today is the expected margin rate of substitution times the payoff tomorrow. In other words, the margin rate of substitution times the rate of time preference, 1 plus R equals 1. This is conditional on all information, so it holds for all assets and all time. So Brown and Gibbons assume a power aggregate utility function. If this is 1, so you end up with 1 minus 1, 0, which is 1. So c to the 0 is 1, 1 minus 1, 1 minus 1, 0 over 0. What you do then is you apply L'Hopital's rule, and that would end up with log utility. So one of the things they want to test is whether this beta equals 1 or not. So we're testing this. There are problems with using consumption because it's hard to actually appropriately measure consumption. So they're going to make an assumption here that consumption is a constant proportion of wealth. So consumption T minus 1 is a constant of wealth T minus 1. So wealth in T is going to be what wealth is left at T minus 1 after consumption, and it earns a market return. So CT equals KWT equals K 1 plus RMT, what we've got up here, WT minus CT. Taking that out through, taking out the K, and remembering CT minus 1 is K over WT, the K and WT minus 1 cancel out, and you get that aggregate consumption is actually just related to the market return at this constant. So what we're going to then do is say, well, this holds then for all assets and all time. And since it holds for all assets, it must hold for the market and must hold for the risk-free rate. So it holds for the market and it holds for the risk-free rate, and therefore these two are equal. And that's what we got there. So we can divide through by the constants and get rid of them. So the 1 minus K, they can all go. They cancel out. And dividing through by 1 plus R the 1 minus beta, you get this expression, and so we can define this as X. It's like an excess return, but in the denominator form rather than difference form. So X to the 1 minus beta, X to the minus beta. So letting X equals this, then you end up with X to the 1 minus beta minus X to the minus beta, or X minus 1 to the X to the minus beta, given the information. You can iterate on the information, so this then becomes the unconditional expectation, and of course the integral of 0 is 0. So they want to show the GMM estimator, but first they start with a parametric estimator. They assume that X is log normally distributed, and they use the moment generating function on the normal. So if Y equals log X is distributed normally, and Cy log X to C is normal C mu sigma squared Y C squared. So we have here, the moment condition of the normal says, moment generating function says E BXC equals C mu Y plus half C squared sigma squared Y. So we've got this equation here, so we can say that this equals this by dividing it up. So taking this as the C, you get 1 minus beta mu y plus half 1 minus beta squared sigma squared Y equals E to, this is the C minus B mu y plus a half beta squared sigma squared Y. taking logs, this exponent equals this, and we isolate solve for the beta. Very interestingly, the beta is just the mean divided through by the variance plus a half, and this is the interesting way to estimate the relative risk aversion. And since log of x is distributed normally, functions of maximum likelihood estimates, because the mu and sigma squared of maximum likelihoods are themselves maximum likelihood. So we can figure out, using the delta method, what the variance of this estimate is. We first differentiate this with respect to the mean, then we differentiate with respect to the variance, and that gives us a derivative matrix of 1 by 2. Then we multiply that by the variance covariance matrix of the mean and variance, and also pre and post multiply by the derivative matrix again. So the variance of the mean is just the variance of x, and the variance of the variance itself is 2 sigma to the 4. And they're independent because mean and variance are independent of normality, because the cross product is just skewness, which is 0 in normality. Okay, and so if you were to do that multiplication up here, that derivative of this with respect to the two parameters times the variance covariance matrix post multiplied by the derivative, you then end up with this 2 times the expected mean squared, the mean squared plus the variance over the variance squared. That's how you get the variance of the estimator. What if the log normally is violated? Well, the estimate can be inconsistent, and when they go test for log normality, they do reject normality. Right? So, hence the method of moments estimator, the GMM, is the way to go. So now describing as a sample mean, the xt minus b, xt minus beta, where beta is between 0 and infinity. They get very careful here. Existence, is there a value of b such that it actually does cross 0? So here's f of b, and here's b, and is there a function? So we're going to look at extreme cases here, right? So we're going to say, well, it stops above 0, ends below 0. And so x to 0 equals 1. Assuming risk individual risk averse, then the expected market return is always greater than RF. Else the risk averse investor would never invest in a risky asset if they didn't expect. So therefore this is greater than 0. So therefore f of 0 is greater than 0. What about as b gets really big? Well, it's going to depend on the sign of this. What's the limit of this? And so we're going to do x greater than or equal to 1 or x less than 1. So we're going to take the limit, break it up into 2 cases. So the whole expression of x is greater than 1 and x is less than 1. So for x greater than 1, then the limit of this is 0. It equals 1 for x equal to 1, and it equals infinity for x less than 1. So hence, this is minus infinity. So by the intermediate value theorem, we have f of 0 greater than 0, f of infinity greater than 0, less than 0. So therefore, it must cross at some point. In order to see whether it's unique, we need to see whether the derivative is always going down. So what are we going to do here is differentiate something where the thing we're differentiating is in the exponent. What I'm going to prove is the derivative of this equals this. So this is the proof. So that y equals x to the minus b, the log of y is minus b log of x. Change in log of y over change in b is 1 on y because it's a log. Change in y over change in b equals minus log x. Do you remember the minus y over g is minus y log x, so substituting it in. So therefore, we get this is the expression. We prove that this is the derivative. Okay. Now we want to see whether it's always decreasing, and probability p is the probability that x is greater than or equal to 1. So therefore, the value of this expression is the sign. The sign of this expression is going to be the sign of this. So positive, negative, greater than 1, so positive, greater than 1, so positive, log of x is positive, plus 1 minus p is positive, minus e, x minus 1 is negative, x minus b is negative, log of x, x to the minus b is positive and log of x is negative. So you got negative plus a negative, therefore this is less than 0. So it starts above 0, ends below 0, and it's strictly decreasing. Right? Therefore b is unique. Assuming x is independently and identically distributed, we can actually get the distribution of b. We use that using Hansen's third result, that is the distribution of theta is d transpose s to the minus 1d, the whole thing inverse. So d is the derivative matrix. So since it's a univariate, so that works out to be the variance over d squared. And this is the variance of the equation here. So the equation here, we're just going to square the actual value here. So to get the variance of this, it's just going to be the expected value of x minus 1 squared x to the minus 2b. Okay, so that's going to be the variance of that equation. So that's what we get here. Just the equation squared will be the variance because the equation has been 0. So you end up with the variance of the line over the slope of the line. So if you go back to the picture, if the variance is very big, then that shows that the standard error of b is going to be big. Since you're dividing through by the slope, if the slope is very small, then it's very low, then you really don't know where you're going to hit. So the bigger the slope, the smaller the standard error. And that's exactly what this shows. You know? So you can see how intuitive the general method of moments standard errors are. The variance of the line over the slope of the line squared. So that method of moments estimating makes us no assumptions about the distribution of x, right, and the whole sum line samples. If the data really was log normal, then the method of moment estimator gives you 99% of the precision. Okay. Which, and if it's not log normal, then you're actually getting the right standard error. So it's very good result. So now I want to do the Brav Constantinides paper. So there was many attempts to test the Lucas model, and they don't quite work out. So what people were using was aggregate consumption, where they sum up all the consumption, yeah? And the CT is everyone's consumption, T over everyone's consumption, T minus 1, raised to the relative risk aversion. So what Brav, Constantinides, Geske do, they test the Lucas model, but they relax the assumption of complete consumption assurance. So therefore, they base the M on individual people's, right? So they do an individual's relative margin rate of substitution, and they sum up over individuals. So they're the two specifications. This is going to be equation 4, and this is going to be equation 9, yep, in the model here. The second thing they're going to do is examine the question of limit participation. So they've got some individual household data, so they're only going to include people who invest in the stock market. So there's a consumer expenditure survey in America, and quarterly data from 1980. In Australia, we have something called the HILDA, H-I-L-D-A data. So they look at it for equity risk premium, both equally weighted and value weighted, and high book to market versus low book to market. So return on high, book to market minus return on low. So equation 4 is the individual's margin rate of substitution. Don't worry about 5, 6, 7, 8. I just went crazy with the Taylor series expansion here. So let's get to equation 9, which is the normal per capita consumption. Yeah. So let's just see how they do. So the result in table 2 uses equation 4, and table 4 does equation 9, and table 7 does 4 and 9 for value growth stocks. Right? So what they find is that, and so what they're doing, the equity risk premium and the value growth. So what they find is that indeed equation 9 doesn't work at all, but equation 4 does do a good job of describing the data. Yeah, and so with values of the relative risk aversion which are reasonable, and that's considered probably less than 5. However, when they go to the limited participation, and these people haven't invested much at all in equity, they don't reject using equation 4, but they don't reject using the consumption model, but the implied rates of relative risk aversion are very high, right? So probably so high that you wouldn't believe it. So I'm going to now go to some suggested extensions. So what they didn't do, they did each of these separately, so why not do them together? And why not use conditioning information, because we've done that with other models and in the Lucas model. So you could have used, could have had the two equations, the excess return, the high and minus low. You could have conditioned based on previous values of those returns and also the margin rate of substitution. And why not combine the market incompleteness and the limited capital market? So these are all extensions that I suggest each year. Someone at some stage, a couple of people took some of these things up, and particularly using the Hilda data to come up with a good consumption measure and imposing some of these restrictions. And thank you very much for your attention.